Linear motors are capable, at least for brief moves, of hitting acceleration pretty hard. As we saw, acceleration beyond a certain point provides diminishing returns, but clearly one of the keys to moving quickly is to use enough acceleration. As we mentioned earlier, there's a fundamental law of motion that we have to take into account, and that is that F equals ma. Now, a is the acceleration that we're going to put into the stage and that it is going to provide to the payload, and that gets the motion to happen quickly, and that's a good thing. But you'll also remember that for every action, there is an equal and opposite reaction. So there is a force that it took to get the stage carriage moving, but at the same time, the stage base is experiencing an equal and opposite force in the other direction. And I mentioned earlier, it's important that your structure of your instrument be stiff, but inevitably it can't be built like a tank for simple economic reasons. And what's going to happen is that when this inertial force is experienced by the structure, it's going to deflect. And that deflection can be exacerbated if we have vibration isolation in the structure. So when we're talking about nanometer level motion, it's very important that we avoid vibration and accelerations from the environment. For all we know, someone at the next lab bench is running a centrifuge or a vortexer. They're walking by and maybe the floor isn't a first floor concrete, maybe it's a fifth floor older building. Things are moving. So to prevent external accelerations from corrupting the image, it is normal and appropriate, with caveats, to introduce vibration isolation into the structure. And the job of that vibration isolation is to prevent those vibrations from affecting the precision part of the mechanism. However, typically the response curve of those sorts of isolators, at least the simple ones, if we look at amplitude versus frequency, is that at low frequencies they'll be pretty flat, and then depending upon which one you've chosen, they'll have a small peak and then they'll fall off. So if you're trying to attenuate frequencies out here, good to go. But if there are any frequencies down in this lower range, there's actually gain there. That is a natural frequency resonance, a spring mass oscillator, as it were. And depending upon what you've chosen, it can actually look like that. So vibration isolation is a double-edged sword. It suppresses some environmental accelerations that are inappropriate, but at the same time, it means that for certain low frequencies, it's actually going to respond rather substantially. And when we talk about these moves, which might happen if this is a 5 hertz peak and you're moving 5 times a second, well, then you're exciting that at exactly its resonant frequency. Things are not going to look pretty. So in many cases, we see customers toning down the acceleration that they use to make moves to lower the frequency and also just to avoid getting the whole thing swaying. Because in a linear motor system, when it sways, it's at a bit of an angle and there's a gravitational mg sine theta force which prints through into the loop. And so when you settle, you'll often see, say, a 5 hertz ringing, and that is the structure and the sway, especially from vibration isolators. Now, it turns out that we've addressed that, and that feature is available at the moment only to OEMs in our SmartStage XY. And the feature we call, being fond of TLAs, which are 3-letter acronyms, we call RME, Repetitive Motion Enhancement. So whenever you have repetitive motion that might be shaking the instrument structure and or its isolators, we can use RME to reduce that effect, but also to dramatically reduce the following error during the move. Now, I'm not at liberty to go into the details of the math of how we do this, and there is a lot of mathematics involved, but the good news is it happens offline prior to the system being turned on for operation in production use. And we simply have to have a very good facsimile of your masses and your moments and your structure and your isolators. So again, that's why we reserve it for OEMs, which we have a partnership with. But in these cases, we can apply the RME during what we call its learning phase, and it iteratively determines a set of stimuli that, in combination with the trajectory, suppress all of this unwanted motion. Now, we can see that very clearly. We can see the unwanted motion very clearly in this prompt, this graphic. So in this case, we have a 4.5 millimeter move, which again is from well to well in a 384 microtiter plate. And the time for the trajectory, now we're using S-curve, but the time for the trajectory is 77 milliseconds. Now, what is the plot here? The plot here is time, not starting at 0, and the vertical axis is the following error. That is to say, when that hits 0, we're where we belong. And so this line here is the commanded. That's what we're supposed to be doing. This is the end of the move. This is where it's stationary during illumination, and now we begin the next move. But as you can see, there's a lot of stuff going on here. Now, it settles to within plus or minus 200 nanometers by here, but if the tolerance is plus or minus 100 nanometers, we don't settle in until about here. And in terms of where the move started, that would be a move time of about 160 milliseconds. And this ringing that you're seeing here is in fact isolator sway. So the inertial move happens, the whole instrument begins rocking, and this is the result. Now, after training with RME and doing the same exact move with the Smart Stage XY having the right information within it, leads to after with RME enabled. I think you'd say that's pretty dramatic improvement. In essence, even for a 100 nanometer settling window, and probably a 75 or maybe even a 50, we are in the settling window at the instant of trajectory completion. And this is, in this case, 77 milliseconds. So we have basically cut the move and settle time by a factor of 2 through this advanced technique. And it's really very valuable. We occasionally refer to systems with vibration isolators as bouncy castles. Everybody knows what they are, and that's what the instrument can act like. And it's very hard to do nanometer precision in or on a bouncy castle. But with RME, we can do that. And we're very proud of that, and it's a feature that is available to our OEM partners.